All right, so this talk is about my new library called Distributors and also about the concept of distributors and how they can be used to unify parsers, printers, and grammars. So first, parsing and its partial inverse, the problem space. So when we define an abstract syntax tree, which is a data type representing the syntax of some language, it could be a programming language or it could be a human language, we then will define a parser, which converts the language from unstructured form, like a string of characters or maybe a JSON value or something, to the structured syntax representation. We'll also want a printer to convert the syntax into its unstructured form. And usually we write these separately, and there's no guarantees that they're going to be inverses. You have to write some tests to check it, and you're basically repeating the logic when you write the parser and the printer. So parsing, the classic definition of parsers in Haskell is that a parser is a function of strings to lists of pairs of strings and things. And useful abstract interfaces were discovered for parsing in the functional Perl about applicative programming with effects. We learned about the applicative class and how it's subconstraint or superconstraint of monad. And so the important interfaces for parsing are functor, applicative, alternative. We'll talk a lot about alternative. Filterable, which maybe we know a little less about. Filterable is like a lot of functions we know from the list functor. It has cat maybes, which lets us remove all the nothings and keep all the justs. And it's dual to alternative. You can think of that because cat maybes, if you reverse the arrow, has the same signature as optional, which is a function defined for alternative. And then two other ones that we won't talk about too much are monad and monad plus, also useful interfaces for parsing. Okay, printing, comparing it to parsing. Printer usually of A is just a function from A to string. Unlike parsing, printing and AST can be total, exhaustive pattern matching. And it cannot be a functor. Instead, it is contravariant. And contravariant functors have a defining method of contramap, which given a function from B to A, gives us a function from f of A to f of B. And you can see how given a function from B to A, we can compose it with the function from A to string, and that gives us a function from B to string. So if we want to unify parsing and printing, and we want to create invertible syntax descriptions, the inverse to parsers are partial printers. Consider the syntax description for a single lowercase character, which is satisfy is lower. If we parse the one character off of our string lowercase a, it should return the lowercase a, or if we print a lowercase a, it should print the lowercase a onto the string. But either parsing or printing a capital A should fail. So satisfy is lower is an example of a partial printer as well as a parser. So what Rendell and Osterman did in their paper Invertible Syntax Descriptions is they simply drop the assumption of functor from applicative and alternative. And now these interfaces will support both parsers and printers. And instead of fmap, we can map what are called partial isomorphisms, which is two functions, a function from B to maybe A and a function from A to maybe B. So in each direction, and it's partial because of the maybes. And that gives us a function from f of A to f of B. Parsers are covariant, so they ignore the function from B to maybe A, and printers are contravariant, so they will ignore the function from A to maybe B. Okay, so the idea is that instead of dropping the functor assumption, we'll use profunctors. And that's because we can unify both covariant and contravariant functors using profunctors. A profunctor is a bifunctor, which is contravariant in one argument and covariant in the other argument. And its defining method is DIMAP, which takes an S to A and a B to T and gives us a function from PAB to PST. So notice that the S to A goes in the backwards direction and the B to T goes in the forwards direction. And we can turn any functor or any contravariant into a profunctor by just new typing it and adding a phantom type in the appropriate place. And therefore, we can think of profunctors as a generalization of both functors and contravariant functors. So we talked about covariance and contravariance, but there's another additional concept of invariance. And I call this the degenerate profunctor trichotomy. A profunctor which ignores the first argument to DIMAP we already discussed is covariance. That example would be Parsers. A profunctor which ignores the second argument to DIMAP is contravariant, the example being printers. Then a profunctor which ignores both arguments is invariant. This is a grammar schema or classification of a data type, but really of two data types, the input and the output. And our example here is data diproxy AB, where there's just a single value diproxy. There's no info whatever at the term level. The only information we get from diproxy is at the type level concerning the types A and B. DIMAP must ignore its arguments and just be equal to coerce. It sends diproxy to diproxy. An example we can consider is for JSON when we're doing decoding and encoding with the ASIN library. We can also do a third thing, which is we can classify the type as a TypeScript type, and that will give us a sort of classification for the encoding and the decoding. So we could have a method TypeScript type and has a constraint, has TypeScript type A, and then gives us back TypeScript type. But what we notice is that A does not appear at all at the term level, only at the type level in a constraint. So A is an argument to TypeScript type at the type level, but there's no need to give it a term of type A. Okay, so Sam talked last time about optics and their profunctor representation. This is the major utility that's been found so far for profunctor class and the profunctor class hierarchy, including strong and choice. So hopefully you guys are familiar with that. And we can represent optics as a function from PAB to PST. And ISOs, we have a constraint that the P must be a profunctor. Lens, we have a constraint that the P must be strong. And prism, we have a constraint that P must be choice. And in the lens library, they actually use a mixed representation with both profunctors and functors, where we have optics are a function from PA f of B to PS f of T. So for ISOs, now we have that the constraint that the P must be a profunctor and the F must be a functor. For lenses, we actually have what's called the Van Laerhoven representation, which means that the P can just be arrow, can just be morphisms, functions. And it's from A to FD, and that gives us a function from S to FT. So the arrow here is our P. And for prisms, it's a little complicated looking, but this is what makes it so that prisms, so that every prism is a traversal, is that we have the constraint that P must be choice and that F must be applicative. Okay. So now I want to talk about partial isomorphisms. We mentioned partial isomorphisms earlier because Rendell and Osterman noted that partial isomorphisms act on both printers on both partial printers and on parsers. So we can represent partial isomorphisms in this optics form because we have a function that we can define dimap maybe, which takes an S to maybe A and a B to maybe T and gives us back a PAB to a PST, as long as P is both choice and co-choice, which just means reverse the arrows from the defining methods of choice. So we can define the partial iso optic by restricting P to be both choice and co-choice, and F to be both applicative and filterable. This way, every prism is immediately a partial iso, and every iso is immediately a partial iso. So whereas prisms we think of as being exhaustive and disjoint patterns, we can think of partial isos as being partial and overlapping patterns. And what partial isos do is they combine prisms with co-prisms, which should make sense because we're adding co-choice to choice. So what is a coprism? A coprism is just a prism with all the arrows reversed. And so a coprism, we don't need really a new thing for it. We can just represent it as if prism STAB is a prism, then prism BATS is a coprism. And we can define operators such that a prism acts on its profunctor representation, choice, and that a coprism acts on its profunctor representation with co-choice. And then finally, using dimap maybe, we can define an action of partial isos on profunctors which are both choice and co-choice. Okay, I'll pause there. Do we have any questions so far? Okay. And does everybody still hear me?
Here, yes.
Okay.
Follow, it's harder.
Oh, well, if we're having trouble following, is there some clarifying questions?
I don't have a specific question. We just like one more time, more slowly.
Okay. So, partial isos.
Yeah, just this slide.
Just this slide. Okay. So remember that choice has defining methods left prime and right prime, which take a PAB to a P either AC, either BC. And co-choice undoes that. So it just says if I have a P either AC, either BC, I can turn that into a PAB with the method unleft. And we can generalize right prime and left prime to any prism, right? Those correspond to the constructors right and left of either, but we can do it for any constructor. And that gives us an action of any prism on a choice profunctor. And so just as we said that the profunctor representation of prisms is choice, the profunctor representation of coprisms is co-choice. And when we combine prisms with coprisms and require that they're both subsets of our optic, then we get partial isomorphisms. So partial isomorphisms are just, we're completing prisms such that they're now invertible. Okay. Hopefully that helped a little.
So choice makes intuitive sense to me because I'm thinking of the concrete profunctor of a function, just the arrow type. And yeah, in my head, if I have a function from A to B, I can easily imagine matching on the either to see if it's a left, then I apply the function, and if it's a right, I leave it alone. But that doesn't work the other way around.
Indeed.
So
but if you
clearly
think
arrow is not a good example of co-choice.
True, but let's think of Kleisli maybe. Let's think of Kleisli maybe. So A to maybe B, then if I have an either and I'm trying to get a maybe out of it, then if I'm matching on, let's say, the left, and it is a left, I'll do a just. And if it's not a left, I'll do a nothing. If it's a right, I'll do a nothing. Whereas the unright is that if I have a right, I match on it and give back just its answer. But if I have a left, I give back nothing.
Okay. But now the relationship between co-choice and those partial printers and parsers makes a lot more sense. Thank you.
Indeed. So yeah, partiality is very important here. And it's kind of what gives us filterability. All right, so let's think about our familiar, hopefully, functor interfaces and ask what of them we have analogs for. So for functor, its analog is profunctor. For monad, hopefully we've heard of arrows. And for monad plus, there's arrow plus. So monad is sometimes thought of as a monoid in the category of endofunctors. And arrow is, or strong endofunctors, I should say. And arrow is a monoid in the category of strong profunctors. But the question is, what corresponds to the applicative, alternative, and filterable classes? We don't really have those available. So let's talk about what is the analog of applicative functors, and they're called, or at least I call them, monoidal profunctors. They're also called product profunctors because we're specifically talking about the Cartesian product here, not any other monoidal product. So a lax monoidal profunctor has a unit, 1p, and a product, star or greater star or less than. I'll call this the sequencing operator. And it's actually equivalent to the profunctor also being applicative. So rather than defining a new type class for monoidal, I just define it here as the combination of being both a profunctor and being applicative using this fancy for all x. Okay. And it has some laws, namely it has naturality laws. This f times g here applies f to the first argument of a pair and g to the second argument. Then if we die map f times g and h times I over p sequence q, then that's the same thing as die map fhp sequence die map g iq. And if we sequence one on the left, that's the same as our unit isomorphism, left unit isomorphism. And if we sequence 1p on the right, that's the same as our right unit isomorphism. And finally, if we sequence right parenthesized, because let's see, we see here we have that sequencing is right associative, so there's an implicit parentheses on there, then that is equal to reassociating for the on the left associated sequence. Okay? And 1p sequencing, this sequence operation is like analogous to the same one for applicative. It drops the value of the first argument and retains the value of the second argument, just like the analog for applicative and for monad. And similarly, this one drops the second argument. And we can define die map 2, which is an analog of lift A2. And notice that it has 3 function arguments because we're fully curried here. So the S to A goes in the backwards direction, and then the S to C also goes in that direction. And then finally, we have a function from B to D to T going in this direction. Okay. And we can define forever P, which is an analog to forever. And we can define replicate P, which is sort of roughly analogous to replicate M, which remember repeats applicative action an integer number of times, except here, instead of giving it an integer argument, I give it a type level argument that the container it's producing, instead of just being a list, is any traversable and distributive T. Now, I know everybody's familiar with traversable, but distributive is probably less well known. But distributive is the categorical dual of traversable. So it has the opposite of sequence A here, called distribute. Okay.
Can we again have a concrete example of a distributive functor to anchor our intuition?
Indeed. So any, let's say reader, any function type is going to be distributive. And so if I have integers to A, that's a distributive functor. So if I say distributive and traversable, what that means is that something to A, that something is going to have to be countable so that I can traverse over the structure. So what a container that's both traversable and distributive turns out to be is a homogeneous countable product container. Homogeneous because it can't contain anything other than its element type, and a product because it's a function from something to whatever. So it's basically a product over that function argument. So that means I could say do new type triple equals triple, or sorry, new type triple A equals triple AAA. And that would be an example of a both traversable and distributive type. Does that make sense? And any product like that would work, triple, quadruple, etc. Okay. Meander is if I have a monoidal T, which is also choice, then I can apply a traversal and have an action on it. Moreover, if I restrict meander to P's which are monoidal, choice, and strong, then this function is invertible, and we get that the profunctor representation of traversals is actually profunctors which are monoidal, choice, and strong, which is a cool result because usually we think of traversals only in the Van Laer-Hoven representation, and it was sort of a little mysterious what the profunctor representation was. And finally, we have a monoidal cons operator. Okay, any questions about monoidal profunctors? Remember, they are analogous to applicative, and in fact, they're directly equal to applicative because they can just be a profunctor plus an applicative. Okay, now we get to finally talk about distributors, which are an analog to alternative. But before we discuss them, let's reformulate alternative a little. We can reformulate it so that instead of having its defining methods be empty and vertical bar, or we'll call that or, it would be 0f and plus addition. So 0f is given an alternative, it's an f of void, and we can just define it to be empty. And we can go the other way. If we had 0f, we can define empty, and we know that f is a functor, we can define empty as absurd f mapped over 0f. The plus, given an f of a and an f of b, gives us an f of their sum, either a, b, and we can define it as left f as x plus y is left f mapped on x, or right f mapped on y. And we can go the other direction. If we had plus defined, we could define or in terms of it, by F mapping either id id. I'll take a moment to pause there and just say, does it make sense how we are redefining our alternative methods
Yes, this
in
is
an
the easiest
equivalent
slide
manner?
so far.
Okay,
Much easier than the previous slide.
okay. So distributor is extending monoidal, just like alternative, extended, applicative. Now it's a class rather than a type synonym. And it has defining methods 0p and plus again, um, doing the obvious things. Now 0p is p of void void, and our plus operator is from PAB, PCB to P either AC, either BD. Okay. And we have these laws that are the exact same laws that existed for monoidal profunctors. So this is also monoidal profunctor. And what it is unlike the monoidal type, which was a monoidal profunctor on products, this is a monoidal profunctor from products to sums. Okay. So we can define some additional methods which have default definitions. Optional P, that generalizes the optional function for alternatives and gives us maybes. And many P, which generalizes the many function for alternatives and gives us lists. Optional is sequencing 1 or 0 of P's, and many is sequencing 0 or more of P's. Okay? The other thing to say here is that the minimal complete definition is nothing because we're going to see that we have a default for 0p and for plus if our p is an alternator, and we'll say in a second what that is, but for now just ignore that. We have this function dialt, which is a lot like our dimap2 for monoidal, except now it's the forward direction that is split up into two functions, and the backwards direction, that's a single function. Okay.
Once again, ask for a concrete
Yes.
example.
Of a distributor. So the best
Yes.
concrete example is Arrow itself. Arrow is, in some sense, the prototypical distributor, COM. And we can take a look
So we
and
don't need
see all the
partiality
different.
anymore.
We don't need partiality, indeed. We don't need partiality for distributors. Distributors can be total. That's a very, very important point. So arrow choice will imply distributor. Arrow 0 and arrow choice. I don't think this should have been arrow plus. I think I need to change that. Some other examples. If we have an adjunction between F and U, then costar of F. If we have an applicative F, then distributor of star of F is, or star of F is a distributor. Arrow is a distributor. So notice that the F doesn't have to be alternative. It can just be applicative. On the other hand, if F is alternative, then we can promote it. Remember, we can just add a phantom type, and that's called joker. And that's going to be distributor. Also, in the other direction, a decidable F, which is a contravariant functor kind of analogous to alternative. If we also add the phantom parameter, that's called clown, then that's also a distributor. So you can remember clowns to the left of me, jokers to the right. Okay. Also, the product of distributors is a distributor. And the composition pro-compose of distributors is a distributor. The next thing I want to talk about just briefly is that we can create a new type class for container types that extends traversable called homogeneous, which is going to be the class of homogeneous countable sums of countable products. So the prototypical example here is list. List is a countable sum of countable products because it's either a list of length 0, which is a 0 tuple, or a list of length 1, which is a 1 tuple, or a 2 tuple, or a 3 tuple, or a 4 tuple, so on and so forth. So it's a countable sum of countable products. And it's homogeneous because the only thing you can put in a list are the items of the list. You can't put an extra integer in there. Okay? And the homogeneous class in some ways sort of classifies our distributors. So we can say homogeneously given a distributor for a PAB gives us a PTA TB. Okay, we don't need to say too much about homogeneous though. All right, so the next thing is alternators and filtrators. So alternators are our number 2 alternative analog after distributors, and filtrators are our analog of filterable functors. Oh, why can't I click? Click this. For some reason, it's not letting me click. Okay, that's okay because we're right here anyway. So alternator, it's extending the choice class and the distributor class and alternative. And it's adding one method, alternate, which given an either PAB, PCD, gives us back a P, either AC, either BD. So this is our case of a lax monoidal profunctor from sums to sums. Okay? And we have a default method if P is, in addition to being an alternator, is also co-choice, then we can get a default definition for alternate. And alternate is where we have the analog of sum, which was defined for alternative, and gives us a list that has at least one element. So it kind of makes sense that this one, sum, is in alternator, because whereas distributor could be total, alternators must be partial. Okay? And so the main thing to think about here is that for profunctors, we're a little bit more complex because we have to distinguish between distributors and alternators. Whereas for functors, there was no distinction. They were equivalent, right? We saw that in the last slide. Okay. Now the filtrator class is dual to that. It's extending co-choice and also extending filterable. And it has a function filtrate, which given a P of either AC, either BD, gives us a pair PAB, PCD. Okay? And so if we look at this arrow, it's actually dual to our plus because this one took a pair PAC. If we were to uncurry it, it would take a pair PAC, PCD, PAB, PCD to P either AC, either BD. And this one goes in the other direction. Okay? Now, what we can also notice is that, I should have gone over these laws for alternate. So left prime and right prime, which were the defining methods of choice, can be defined in terms of alternate by just ignoring the right, doing the left, or vice versa. 0p, we said, could be defined as empty, right? Because we're extending alternatives, so we have empty. And x plus y, we get by doing alternate left or alternate right y. Okay? And similarly for filtrator, unleft is first dot filtrate. It's this first one here, and unrate unwrite is second.filtrate. Okay. So the next thing is step by, which is a separator combinator. So now we can actually kind of start creating combinators from these. So first of all, I'll define step by as just a helper type, which has a begin by, an end by, and a separate by. So this is going to be usually like a comma or something, and these could be open paren and closed paren. And we have a default step by, which just assumes that begin by and end by are 1p, right? Or nothing at all, don't do anything. And we have no sep, which is even the separator is nothing. And then we can define our function 0 or more, which given a step by is going to give us from a PAB to a P of list of A, list of B, such that 0 or more, if we separate by no sep, could be the same thing as many P. And same thing with 1 or more. Notice that 0 or more can work on a distributor. 1 or more is partial, so it has to work on an alternator. And not only that, but we get chain L1, chain R1, chain L, and chain R, which if you've used these before in parsers, what they do is they also take a list of inputs, but instead of giving a list output, you give it a binary constructor. And here, the way we do that is by passing in a partial isomorphism, which is a binary constructor. So notice it has A, comma A, B, comma B, and produces a B. We give it a step by, and given a PAB, it gives us a PAB. So this sequences 1 or more times. That's what the 1 is standing for. And you have to give it a binary constructor pattern. So that's going to be like in our expression AST, we have like a plus expression. So the associated prism plus will be our partial iso that we plug in here. And similarly, chain L and chain R, and the L and the R is just for whether we're left associating it or right associating. And for chain L and chain R, we have to give it an additional nilary constructor pattern for the case when there's nothing, when there's 0 things to sequence. Okay. And the next thing to talk about is this tokenized class. And this is a kind of funny one. It's saying for a P, all it really tells us is that we can determine some A and B from P, and that we have any token, which gives us PAB. And the main thing that we want to consider this for is for token stream printers and parsers, that when we sequence a single token of any classification. So this is like a wild card. Anything, any token will pass it. Okay?
Wait, so I'm trying to understand what A, B, S, and T mean now that we've switched from some very abstract type classes to something that clearly means parsers. So at least one of those 4 letters is going to be string. Maybe A is a string and B is a token from like a some type of like it's either comma or left parenthesis or something.
Both A and B are going to be whatever the token type of your parser is. So if you've already, let's say, tokenized it so that it has some token like enum, right?
Mm-hmm.
Left paren, right paren, blah, 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 blah. This any token will be a P, my token. And we can see that because if we have a tokenized CCP, and then we say we want a token which satisfies a predicate, then we get out a PCC. Okay, and so you should think of this C as being, for example, a char. So if we had a char parser, right, that's parsing a string of chars, then we say satisfy is lower, right? That was our earlier example. It'll give us a P char char. And where the strings come in is this tokens. So token will sequence a single specified token. So as long as that token has an EC instance, then we can say, I want the token lowercase a, and we already know what the input is, so we just don't even bother giving any result from that. And similarly, we can do a stream of tokens if our P is monoidal, because we can sequence them. And this tokens function is useful as a default definition for from string method of isString if our P is tokenized char char. Okay? Does that help with the intuition for tokenize?
So I was trying to understand STAB, but now C has entered the picture. So, okay, so C is char, list of C
So first
is
of all, there's
string.
no S and T. There's just A and B, right? Because we're just talking about the profunctor. We're not talking about optics here.
But earlier you had separated by, which did use STAB, and I was confused by that. Okay, yeah, chain. In the chain rule, you have a partial ISO where you have AB, AA, BB, and you said it was because it's a binary constructor. So for the output type, it makes sense that I'm parsing something into two things, the left argument and the right argument. But I don't understand why is the input type also a pair, and what are A and B? I would have expected to parse like a string into two subterms.
So the A here is going to be, let's say, your expression AST. Let's call it EXP, right?
Mm-hmm.
The B is also going to be the same expression because the input and the output are both expressions because the input is the input to printing and the output is the output of parsing. And we're printing both the expression. We're both printing and parsing our expression AST. So while this is very general and allows us to use separate A and Bs, in practice, we're always going to have them be the exact same.
Okay.
And so an example of one of these partial isos is your add branch of your expression AST, whose arguments is add exp exp.
Mm-hmm. So the add xexp constructor is like if it was just a term data type that only had this one constructor, add exp. Well, okay, data exp equals add exp. That is indeed isomorphic to the pair exp comma exp.
Indeed. And if we did like make prisms on that constructor, it would construct a prism of exactly this form. Right?
A prism,
Make
not an
make
ISO.
prisms constructs prisms with tuples.
Yes. Okay, okay. In the regular lens library, not the profunctor based or distributors based. Okay, so now if my expression data type has more than one constructor, not just add, then it is not the case that add exp is isomorphic to a pair exp, and that's why we need a partial isomorphic. Because
Well,
if
that's
I
why you
have an
would need a
expression,
prism.
then maybe I have the add constructor, and if so, I do have a pair.
Yes. And going back to tokenized, we had any token as the defining method. Satisfy is we can, instead of just any token at all, we can say a token which satisfies some Boolean condition. And then we can say some specific token or some stream of tokens. Okay. And then finally, here's our example to make things clear. We have printor. Here's our string S type. Here's some F, which is a container. It's probably going to be list or maybe. And our A and B. Notice that the B doesn't appear anywhere in the definition. It's just a phantom type. And the A appears in contravariant position, right, before as the input to the arrow. Okay? So a printer is a function from things to containers of functions of strings to strings. And it's a degenerate profunctor, which is constant in its covariant argument. And it has all of the instances we want. If our string is cons of our characters, so for instance, list is a cons of its items, then we get that our printer is tokenized. If the F is alternative, then the printer is an alternator. And if the F were just applicative, the printer would still be a distributor. The printer is a filtrator. It's choice, co-choice. It's co-choice because it's, well, actually it's co-choice no matter what, because it ignores one of the arguments. It's contravariant, etc., etc. Okay.
So with
The
a name
next,
like printor, I would have expected the implementation to be like a arrow string. So it's to a maybe string because it's a partial printer, and it's to a maybe of a string to string. Like, is it so that you can concatenate them easily?
yes, yes. Otherwise, we would need, if it was just a string, then we would need to give it a monoid instance in order to get all these. But since it's a function, we can just use, since it's an endo function, right? We can just use function composition as our monoid operation. And there's the whole argument about efficiency of, what do you call it? The like Cayley representation of monoids. So,
Okay, so semantically, this function from S to S, it prepends the string representation of A to the tail that it is given as an argument.
yes.
Cool. Thank you.
I mean, it could do anything it wants, but that's generally how you're going to use it. Yes. And that's what this, when I have cons, it literally cons is onto the beginning. So, okay, parsor in the opposite direction. Again, we have our string type, our container type, and our input and output types, and the input doesn't even appear in the definition. And this is just the classic definition for parser. It's a function from strings to containers of pairs of things and strings. And it has all the instances we want. I should note that both printers and parsers get the isString instance because we can just give it from string equals tokens. Okay, so I'll pause there and ask if anybody has any questions. Okay.
How does the printer have a functor instance?
How does the printer?
Yeah.
Good question. How does it have a functor instance when it doesn't even have B in it? So the answer, we can actually take a look. Well, it's deriving functor, but what does it do? It just ignores its functor argument, right? It just coerces.
Yeah, okay, yeah. But then the parser, it also has a functor instance, right? Isn't it? Or
Yes.
is it switched?
And it has a bifunctor instance and a profunctor instance. Isn't that weird? So it's both covariant and contravariant on its argument A because it ignores its argument A.
Oh, because it's not okay. It's not in the position. Yeah, got it.
Yeah. And that's why we can be, for printers, both contravariant and a
Yeah.
functor. Phantom variant, or I call it invariant, right? So you're covariant if you change the same way as the underlying change, contravariant if you change the opposite way as the underlying change, and invariant if you don't change given an underlying change. Okay.
I had another question.
Yeah.
It's very common to find parse grammars that parse to, I would say, multiple parse grammars that parse to a singular internal ADT. So these two representations are no longer isomorphic. So how does this transformation, or is there some way to pick like which print you want to use, or what's happening?
Well, that's one of the reasons this F can be alternative. So you can get, in fact, all the possible prints of a given thing and have it be, in fact, an infinite list of possibilities. So imagine that we had in our language parentheses, right? So one thing you could do is just keep adding parentheses and it's the same expression, right? You just keep nesting more and more parentheses on and it's equivalent. And if we used F as a list, it might end up being an infinite list because every single parenthesization will get spit out. Or if we had like pretty printing, then we might say this one is the best one and that's the first one or something like that. So we can use this F structure to handle that in some way.
I see. And so the ordering of that structure implies some sort of preference. That's what you're suggesting?
That's one way to use it, yes.
Thank you.
Okay. So we talked about printers and parsers. Now let's talk about grammars. So this is our money shot application of distributors. So we'll talk about a Backus-Naur form grammar, or BNF, is a format for specifying context-free language syntaxes. And they're built from terminals, which are just strings, and which must exactly match the characters in the input. Non-terminals, which are also strings, but strings that refer to rules, which are production rules, which include a start rule, which is where you start the grammar, and sequencing, which is just putting things next to each other, and alternation, which is or. It can be either this or that. And an extended BNF, eBNF, extends BNFs by adding repetition, optionality, and grouping, parentheses, like we said. And regular expressions, or regex, is a format for specifying regular language syntaxes that was introduced by Stephen Kleene. All right, so we have a prototypical example of grammars. We'll define an eBNF for regular expressions, and it's actually going to be a BNF that's extended by regular expressions so that it's self-specifying. So let's take like a minute to take a look at this specification of regexes. We start at start, and then it says this is a non-terminal regex, so then we jump to regex. This is non-terminal alternate, so we jump to alternate. Okay, then we have a sequence, and we're sequencing. An open, this paren is actually grouping, so we have a vertical line, and then another sequence, and this clean start. Is everybody familiar? Is everyone relatively familiar with regular expressions? Clean star means 0 or more, so we can have one or more sequences here.
I find it so funny how, like, of course we're all familiar with regular expression. This is the very complex category stuff we're not familiar with.
if it was me on the other end of this lecture, this is the part that I would get very lost. Any is the wildcard character. Atom is a non-terminal, fail, class in, class not in, category not in, or char, or any, or parenthesize. Sequences are a 0 or more expressions. An expression is either a terminal or an optional or a clean star or a clean plus or an atom. Optional is an atom followed by a question mark. Clean plus is an atom followed by plus. Clean star is an atom followed by star. Fail we see is /q. We have to slash the slash. And non-terminals, where non-terminals is /q and then followed by a open brace followed by 0 or more characters followed by a closed brace and parenthesized. Is there any questions on this grammar for regexes? Okay. So one interesting thing about this is that we can't define a regex for regexes because regexes are not a regular language. They're a context-free language. All right, so let's talk about embedding grammars in Haskell. All right, so we have now this grammar type. Type grammar is for all P, grammatical P, PAA, and grammatical we'll define in a second, so just keep that in your head. And I define this grammar, which you can pronounce like a pirate, and it's just a function of grammars, but we kind of have to define it separately because if we said a grammar A to a grammar B, then it wouldn't know that these P's are the same. Okay, so what is this grammatical class that we're defining grammars in terms of? It's extending our already defined classes, alternator, filtrator, and tokenized over characters, and also that we have isString for terminals. So because we have alternator, we have all the regular expression combinators, right? Because alternator gave us sum, which is like clean plus, and distributor gave us many p, which is like clean star, and alternator gave us alternative, which gives us our alternation operator, and monoidal gave us our sequencing operator. Okay, and we add a couple more regular expression operators. We have in a given class, so just say any one of these letters, or not in a given class, in a given category. This is not the category theory category. This is the general Unix category of a character or something like that, or not in that category. And we have a rule or a recursive rule. So you can see how these are giving us an embedding in Haskell of our EBNFs, which are extended by regular expressions. And we can see a very useful example of a grammar in this grammar for regex. We already saw what it looks like, but let's see what it looks like embedded in Haskell. And we'll see that it follows exactly the grammar, and it should be very familiar from applicative parsing, the style that we use. So first of all, we'll say overall regex grammar is a recursive rule that given a grammar for regular expressions applies the alt grammar on regular expressions. What's the alt grammar? It's chain L1 of alternate, actually, before we go to this, let's actually take a look at what the regex type is. It's pretty simple. Here's our abstract syntax tree, our AST for regular expressions. It has terminal. Sequence is one of these binary constructors. Alternate is another binary constructor. Okay, and we have unary constructors, clean up, clean start, clean plus. We have the wildcard character dot. We have in class, which is with square brackets, not in class, which is square brackets with the caret. And we have in category, which is / lowercase p with a category, and not in category, which is capital P. And to that we add non-terminals, which is /q, open brace rule name, close brace, and fail, which is just /q with no braces. And we have terminals, which are just literal strings or escaped characters. Okay, so we were looking at the regex grammar, and we were actually, you know what, let's take a look instead at slightly newer code. I like this one better because it has the vertical bars. So just like our rule for atom was non-terminal or fail or class in or class not in or category in or category not in or char or any or parenthesized, our rule for atom, it's a grammar, so it takes in a regex. And given that regex, it's either a non-terminal or fail or class not class not in or category not in, or a single character. And here we say it's a terminal applied to a single character. And then we cons it onto the empty string. Or it's the any wildcard character. Or finally, here's where our recursiveness comes in, because we're applying parentheses to our regular expression grammar. Okay, and notice all these are generated prisms. And notice that we can use string literals, and notice that the way we apply them, instead of what you're used to from applicative parsers using fmap, we're instead using our partial isomorphism mapping operator. And so you can just follow the definition of the grammar and kind of translate it into Haskell in the most obvious ways. And what's nice about this is that each little thing is self-contained, and you can kind of test each small parser. And while you're building the big parser, you can also test the printers. You can also print out the grammar. So it makes it a very nice and useful playground when you're designing front-end language, designing the front end of a language. Front end meaning the syntax, not the semantics. And you can see here we have the rules for escaping and for literal characters. If we are in this reserved class, then we need to escape it. So we add a slash. And since this is Haskell, we need to escape a slash in Haskell. So this is actually just a single slash, and then in char's reserve. So on and so forth. And these are all just following exactly how the grammar looked over here. Okay, and then the last thing we can do is using a grammar, we can generate a parser using the read_s type, or we can generate a printer using the show_s type. And what's cool is the definitions are really simple. To generate a reader, we just run parsor. To generate a show S, we just run printor. And this read grammar is just using gen read S, and this show grammar is just using gen show S. We can also generate from a grammar a regular expression as long as we don't use a recursive rule. Otherwise, obviously, it's going to infinite loop. But if we don't use any recursive rules in our grammar, then we can turn it into a regular expression. And if we do use a recursive rule, we can still generate a grammar, which is just a list of regular expressions with rule names. And finally, we can just print the grammar, which is using gen grammar. Okay, so it's 9:09. We have, I guess, 5 minutes left. And the only thing I'll say is that also, in addition to partial ISOs, which we've discussed, remember they extend prisms. I also added some optics types which have been discovered before, which include grates. Grates are dual to traversals, just like we talked about distributive earlier. Grates are to distributive, how traversals are to traversable. Withers are like traversals, but instead of applicative, they have alternative, and they can be used as filters. Monocles generalize both grates and traversals, and they are for monoidal P's, hence the name monocle. And these two I have introduced diopters corresponding to distributors, and notice that they have applicative. And bifocals are these bidirectional parser optics, and they are alternator and filtrator, and also alternative and filterable functors. Okay, so I made it through all the material I wanted to, which is pretty surprising. I'll ask now if you guys have any questions or anything you want me to discuss.
Thank you, Ethan, for this presentation. I was impressed how you managed to connect the very abstract nonsense of category theory with some very practical things like with Squeal, Postgres, and with distributors, parsers, and 3D printers. Very impressive. So obviously the advantage of using something like that, the main one of this is that you can define the parser and the printer at the same time rather than separately, so you make sure that they match. But with Squeal, like the main advantage, to me at least, is that when you're constructing the terms, it's very composable. You can define small pieces and reuse them in another query elsewhere, whereas with the other SQL libraries, it's harder. And so because this library is also based on category theory, I was wondering if there was also that kind of advantage, if it's more composable than the competition.
Yes, I believe so. It's very composable, and I want to say that the abstractions are more general than just their utility as invertible parsers. And I haven't really explored what other applications there might be, but certainly since applicative and alternative are very useful, I would imagine that distributors should have the same level of, a high level of utility as well, and be very composable. One thing I want to say about composability, we talked earlier about exhaustive versus inexhaustive in the context of printers, and that distributors could be exhaustive, but the inexhaustive style is much more decomposable, right? We can look at just small pieces, on the rest of it just fail. Whereas if we want to be exhaustive, then it's less decomposable. We have to define everything all at once. We have to handle all of the branches of the data type. So that does inhibit decomposability.
Thank you.
Okay. Thank you guys so much. I appreciate your attention.
Thanks for coming. We don't often have guest talks. I'm glad I managed to get you.
Thank you.
Stop recording.
Thanks.